So we're going to finish off with our last couple of examples dealing with the lepton family number. So we have two more reactions here. So we have this neutron decays into a proton plus an electron plus a muon antineutrino. Once again, we're going to check our 5 conservation laws. So we're going to check charge, baryon number, electron lepton family, muon lepton family, and tauon lepton family. So in terms of charge, we have our neutron. Well, the neutron's going to have no charge, and this is going to decay into a proton, which has a charge of +1. We have our electron, which has a charge of -1, and then we have our muon antineutrino with a charge of 0. So we do uphold conservation of charge. We're going to have 0 equals 0. We're happy with that. In terms of the baryon number, well, for the baryon number, we have a neutron. It's a baryon. It's got 3 quarks, so it's going to have a baryon number of 1. We have our proton, also has a baryon number of 1 because it has 3 quarks. And then our electron and our muon antineutrino, since they have baryon numbers, since they're leptons, they're going to have baryon numbers of 0. So we do have 1 equals 1. The baryon number is conserved. Nice little tip for exams. Anywhere you're putting a baryon number of 1, all the lepton family numbers are going to be 0. Because if it's a baryon, it can't be a lepton. Baryons are made up of quarks. Leptons are not made up of quarks. So what that's going to tell us is for our neutron and our proton, since they are not leptons, they are made up of quarks, they are going to have lepton family numbers of 0 across all 3 families. And that's a nice way just to take care of things quickly. Now, our electron, it will go in the electron family. It will have a +1 since it is just a regular lepton. It's not an antilepton. And then in the muon and tauon families, we're going to have nothing. And then lastly, we have this muon antineutrino, so it's going to go in the muon family. It's going to go in as a -1 as an antilepton. And then we're going to have 0 for the electron and tauon families. Let's look. Well, our electron family is 0 equal to 0 plus 1 plus 0. No, it's not. The electron family is actually not conserved. Neither is the muon family because 0 is not equal to -1. But then the tauon lepton number, that's okay. So this reaction is not permissible because it doesn't conserve the electron family number and it doesn't conserve the muon family number. So we have violation of electron and muon lepton numbers, or family numbers. The previous example that we did, as I mentioned, had to deal with beta positive decay. If you're really clever, you might see that this is almost similar to beta negative decay, and it is. Like in beta negative decay, you have a neutron that does decay into a proton and an electron, but it decays into an electron antineutrino. So if this was an electron antineutrino, all of our conservation laws would hold. So that's the only problem with this. It's attempting to be a beta negative decay. They just put the wrong type of neutrino, the wrong family of neutrino there. Right, and the last one, we have a neutron plus a proton decays into an antimuon and a muon neutrino. Once again, we're going to check all of our charge rules here. Our conservation rules. So we've got the charge, baryon, electron family, muon family, and the tauon family. Right, in terms of charge, so the neutron doesn't have a charge, proton has a charge of +1, and then our antimuon, it's going to have a charge of +1 as indicated by the superscript, neutrino, charge of 0. So 0 plus 1 is equal to 1 plus 0. Yep, I can get behind that one. In terms of the baryon, so the neutron, it is a baryon. It will have a baryon number of 1. The proton, it is also a baryon. We'll give it a baryon number of 1. The antimuon and the muon neutrino, they are both leptons, so they are both going to have baryon numbers of 0. Well, we already broke the rules here because we have 2 on the left, 0. Baryon number is not going to be conserved. Now, if this question was just asking you, is this reaction possible, we wouldn't even have to check the lepton family numbers. We already found a violation of the conservation of baryon numbers, so we could definitively say this reaction isn't going to proceed. We're just going to check the lepton numbers, just again to give you that familiarity with how we check those lepton family numbers. But realistically, if it was asking you about the validity of the reaction, we found that it's not going to be valid. But just for completeness. So I mentioned anywhere we have a baryon number, that's going to have a lepton number of 0, because if it's a baryon, it can't be a lepton. So on the entire left side of this reaction, all the families are going to take zeros for the neutron and the proton. So for the anti-muon is going to take a lepton number of -1 in the muon family, and then a 0 in the electron and tauon families. And then lastly, we have this muon neutrino. It's going to take a +1 in the muon family, 0 in the electrons and the tauons. So our electron family is going to be conserved, zeros across the board. The muon family, we got 0 equals 0. It will be conserved as well. And then tauon family is certainly conserved. So we have 0, as we have zeros across the board. So in this reaction, the only thing that's actually violated is the baryon number. So we have violation of baryon number, or baryon number conservation. So in IB physics, there's those extra conservation laws you have to know about. You have to know about conservation of the baryon number and the lepton number. And then conservation of strangeness is more to look at how the interaction's proceeding, whether it's proceeding by like the weak nuclear force or not. But there are a lot of conservation rules you have to remember. On IB exams, they don't ask you too much about them, so it's not a huge thing you have to know about, but it is something you have to know about. So just keep it in the back of your mind. It's a lot of tedious work, but thankfully it's not a lot of complex calculation.